head with the 3 normalizing term. Pi 2 is taking the viscosity and formulate a dimensionless pi term. Now, if you have to do that by the long way, then you do lose 5 minutes, and I can't help you. But can you do that by inspection? We've done that many times. Anytime you see a viscosity, what should blink in your head? What dimensionless perimeter that we have studied so much that must be resulted from viscosity? If you have to think, then you're a little behind. The Reynolds number. Is that clear? Is that obvious? It's the Reynolds number. Can you see that? Or if you don't, then I have to stop. It should be a given. It should be a given. You don't have to go through the A, B, and C exponent. So the Reynolds number is simply then the viscosity term mu, density, diameter, and the velocity. What's the velocity? What's the velocity? What combination of diameter and omega, RPM, give me velocity? The product. Two seconds. This is 5 minutes. You run out of time, those are the reasons that you run out of time. Right? Any question on how you do that by inspection? The next one by inspection is a little bit more tricky, but I think, although I'm not sure, among your homework we've seen something similar to this. So what's the unit of gravity times the height? In SI? Meter squared, second squared. What combination of diameter, omega, and density will result in meter squared per second squared? We just said this combination give me velocity in meter per second. So what is the answer by inspection of what the denominator is? D squared omega squared. Density is not needed. If you raise the density to the exponent, that will be 0. So this is the difference between having enough time and not enough time. Do it by inspection. You will have more time to work on another part of the test. Okay, the next part requires similitude of using the result from part A. So if you didn't do part A right, part B will be wrong because they propagate. And you will lose credit because of that. So part B said, I have a pump with this characteristic. It's one geometry, and then I'm going to build a bigger one where in my bigger prototype, I like to have the same pressure rise, same head, that's the H. But my dimensional, due to similitude, my pi term, that's the head, is the pi 1 that you get here, must match between my model and my prototype. And my Q, you can call it the pi 3, which is given, must also match, such that using those conditions from part A, with the pi 2 term known, find a new Q2 in feet per second, where my rotational speed for the new pump is 2,500 RPM. That is matching, and I won't solve the problem for you, but give you the answer. Q2 a little less than 600 cubic feet per second. And the way you approach this is to match dimensionless head, which is from part A, dimensionless Q, which is given in part A. And when you do, the final answer will depend on D2 and D1, which is a ratio you can determine somehow. I won't tell you how, but when you work the problem, that will come out. Do you have enough information on the board to rework the problem? I didn't do it for you. I think the rest is algebra. Questions? Questions? On the first two problems, anyone? Okay, with the remaining 5 minutes, I'd like to start our new topic, new chapter, going way back to chapter 4 now. Is for the rest of the semester, between now and final, we're going to look in detail what we call dimensional analysis, differential analysis, which if you look back at the roadmap, control volume, global approach, very simple momentum equation. Get the force on holding an engine to produce thrust in the back of an envelope, 10 minutes calculation. We look at dimensional analysis, experimentation. What is missing is what you can justify someone to pay you a salary of $70,000, working at Siemens or Rolls-Royce analyzing flow in an engine. That, by and large, reduced to a very intricate, very complicated and sophisticated differential analysis, whereby I want to know everything inside my engine. You give me a point in the engine, at the exit of the fan, in the nozzle, I'm going to tell you the velocity in 3 components. I'm going to tell you the pressure, I'm going to tell you the temperature. Anything you want to know, I'm going to calculate it on a computer. All right? And I hope using that analysis, when you start changing your geometry, I can get an answer to tell you this geometry change is good or this geometry change is bad. That is what we are set up to do for differential analysis. So as a backdrop, an introduction, and just to relay what we did early in the semester, where have you seen that before? Let me dictate what I meant by differential analysis. And then I'll ask that question again. So another equivalent description in layman term, instead of calling differential analysis, which is kind of intimidating, is equally correct to call it small scale. I'm now shrinking my analysis size space into a dx, dy, dz. Before it was a global approach. Now I'm looking at fine scale of differential element. It turns out the physics, what is physics? Well, conservation law, that's the physics, are the same. So what are the physics? What are the conservation law that you have done? I'm sorry? Continuity, conservation of mass, yes. And then? Energy. But before energy, I would like to hear something first. Momentum. It's the same old, except instead of applying to a inlet and exit of a nozzle, now I'm applying to a small dx, dy, dz, or what I call infinitesimal, very small. Control volume. So I'm going to have to redivide all my continuity equation and momentum equation now applied to a dx, dy, dz space. The result of that is what we call the equation of motion. equation of motion because that set of equation, not just one, but continuity, momentum, and energy, is what I need to solve to get all the parameters I want. What parameters? Velocity, pressure, temperature, you name it, I can spell it out for you. The motivation, the why is, with that I can tackle any problem, not just invisible problem, but more importantly, viscous problem. So the first task is to develop that set of equation of motion. And that's what the next couple of lectures is about. And when you see those equations, and you have seen a small iceberg of that via the Euler's differential equation, but that is the simplest form you can tackle. And the equation is very ugly. If you look at that, you just throw your hand up and say, I don't want to see it again. And it's nonlinear, it's very difficult to solve except on the most powerful computer. And that led to what we call CFD. And in your senior elective or senior design classes, you will have opportunity to do that. It's called computational, that's C. Fluid dynamics. Those are commercial programs that if you work for Pratt & Whitney, you pay the software developer a licensing fee to use them, and you will use them to solve the equation on the computer numerically. The other motivation which we have done is it turns out by assuming some assumptions such as Bernoulli, I can obtain some useful post-form application of this equation of motion. And that's the Bernoulli, which you have seen back in chapter 3, by way of courtesy of the Euler's equation for